Hello! We learned about as much as we could about differential equations of order 1. We tried it analytically, we tried it numerically. So now it's time to look at differential equations of higher order, because there are such equations and they are useful. So it is useful to know something about them. The problem is, when you start worrying about differential equations of order 2, 3, and so on, you find that they are much harder to work with compared to differential equations of order 1. For instance, there is no such thing as separation. In fact, there is only one group of higher order differential equations that we can handle well, and that's so-called linear differential equations. Let's have a look at the definition. So, linear differential equations are equations that can be written in a specific form. We can see it in this first centered line over here. And before we look at it closely, let's recall something from linear algebra. When we have some objects, we can call them y1 through yn. In linear algebra, they call them vectors. These could be matrices, polynomials, vectors from Rn, whatever. We can combine them together in many ways, but in linear algebra, we only care about one type of combinations, which is linear combinations. So we are allowed to multiply these objects by some constants, typically real numbers, but it could be also complex numbers and so on, and then we can sum them up. So these are linear combinations. And the whole theory of linear algebra essentially worries about things that can be combined or are combined in this way. Of course, when A is negative, it's actually subtraction, so subtracting, adding objects, multiplying them by constants. That's what we are allowed to do. And when we look at the definition of the linear differential equation, we can notice that there is the nth derivative and n minus first derivative and so on, all the way to the first derivative and to the original function on the left-hand side. And they are multiplied by some coefficients and summed up. So that's exactly a linear combination. There is a subtle change. In linear algebra, we work with static objects. A matrix, that's a static object. It's there and it's sitting there doing nothing. But here, we are working with functions. We have a function y, the unknown function, and the derivative, which is also a function. So we are looking at them at different times, and perhaps at the different times, we would like to combine them in slightly different ways. So we have to allow these coefficients, a1 through an, to actually change in time. And that's why in the definition you can see that, for instance, a0 has a variable next to it. Actually, properly, we should be also writing yx and y derivative x and so on. But it is assumed automatically that those y's, they have variables with them, so we do not write them. But we emphasize it with the coefficients because there it is something new, something unexpected. So the coefficients in the linear combination, they can change. And we will not worry really about it too much, and soon we will get rid of it anyway. But in general point of view, we are allowed to change the coefficients as we move through time. Now, when you look at a differential equation like that, you may notice one change. Previously, we really liked to have the highest derivative isolated and everything else on the other side of the equation. Here we do it differently. We put all the y's on the left. There is a reason for that. I'll be talking about it soon. Essentially, this is for convenience and for interpretation. So there is a good reason for that. Okay, let's have a look at some simple example. Let's say y double prime is xy prime minus 13y plus e to x. So I claim that this is a differential equation that is linear because the unknown functions, they are all just multiplied by some coefficients. Here's a coefficient, x, it's changing, 13 coefficient, and they are added or subtracted. Of course, properly, I should write it like that. Y double prime minus xy prime plus 13y is equal to e to x. And now we can see all the y's on the left, and there is something left on the right. So this is a linear equation. On the other hand, if I try, let's say this one, y double prime is y over y prime minus sine of y plus e to x. then this is definitely not a linear differential equation because the function y is actually acted on by the function sine. We have a composition here, function y is the argument of sine, and that simply is not allowed when we are forming linear combinations. Here the unknowns, the unknown function, its derivative, they are divided. Again, that's an operation which is not allowed in the form of linear combinations, so this is not linear. Definitely not. Okay, now we know what the linear differential equations are, and let's ask some good questions. And the first good question is, can we solve them? The familiar question of existence and uniqueness of solutions. And it turns out that for linear differential equations, the answer is definitely whenever we have a chance. So let's have a look at the slide. This is the key theorem on uniqueness and existence, and I will not really prove it because the proof is not easy, and it can be found in books anyway. So what it says, we have a linear differential equation written in the familiar form now, and it says that if the coefficients are continuous on some interval, which is, let's say, a very basic demand. If you have an equation and the coefficients aren't continuous on the interval where we're looking, then you are in big trouble. So this demand is very mild. It's a baseline demand. So if the coefficients on the right-hand side are continuous somewhere on an open interval, then we have solutions there. And not only that, we can choose initial conditions in any way that we want, and we will have a particular solution on the whole interval I. So this is much stronger than the Picard theorem on uniqueness and existence, which was local. Here, the solution is guaranteed on the whole interval. By the way, talking about initial conditions, when we have an order n linear differential equation, then it requires n initial conditions. So we specify the value for the function y at some time x0, and also the value at the derivative and of the second derivative and so on. And if we need n conditions, then the last condition is about the derivative of order n minus 1, and then the numbers fit. Okay, so it all fits together nicely. For instance, if you have second order differential equation, which is typical in physics and so on, then you would need two conditions, two initial conditions. One of them is about y, and the second is about y derivative. See, so we end up sooner than we get to the second derivative with the initial conditions. Okay, so that's the key theorem. And actually, I will be using it also, but it's an optimistic theorem. You know, it puts us in a good mood. These linear differential equations seems to be working really well, and they are working well. They are the best equations. In fact, there are many different kinds of equations. There are algebraic equations, differential equations. So you've got recursive or recurrent equations, matrix equations, functional equations, variational equations. I mean, many types of equations. And for each of them, there is a specific group, linear equations, and these are always the best. And even when you are proving the properties of such linear equations, it's always the same in all those different types because there is this underlying notion of linearity. Let's recall something. In linear algebra, we are looking at linear systems of algebraic equations, and we learned many things. For instance, when we look at the homogeneous case, then this is the simplest one. This is really nice and easy to handle. We can get complete information easily. And it turns out that when you look at all the solutions as a set, it's a subspace. So let's say that you are working in 3D, and the set of solutions could be a two-dimensional plane. That's quite possible, passing through the origin, for instance. And we also learned that when we are solving a non-homogeneous system, then we can simply ignore the right-hand side. We solve the so-called associated homogeneous system. We find its solution, which is a nice subspace. And then we find some solution of this non-homogeneous system, and use it to shift this homogeneous space of solutions. So what we get is this. Here is some solution, let's say this one. It's a particular solution, just one solution that we found somewhere of this system. And we take this as a movement, as a shift of this set. So this point moves here, and this whole set moves here. And that would be the set of solutions of this non-homogeneous system. This is what is proved in linear algebra, and it's a very nice property. And as I said, this is true for any type of linear equation, in particular for linear differential equation. Let me show it. Let me prove it. And if you still recall something from linear algebra, you will see that the proofs are actually going along the same lines as they did in linear algebra for such nice systems. Okay? So let's have a look at our first statement. We have a homogeneous linear differential equation. So on the right there is 0. And it says that if I look at all the solutions on a specific open interval, then this set is a linear space, or a vector space, people call it differently, of dimension n, where n is the order of the equation. Okay, before we prove it, let's do some preparation. When you are talking about linear spaces, what does it mean? Well, we have to prove some properties like commutative law, associative law, and so on. I think there is like 8 properties, but some people lump some of them together and they get 7, whatever. And this is a lot of work. There is an easier way how to prove that something is a linear space. Namely, we can show that it's a subspace of a larger linear space, which we already know. So we save a lot of work. So are there any linear spaces of functions that we know? And well, perhaps you don't know, but there are generally known, at least for mathematicians, some spaces of functions that are of interest. So we have an interval I that we are interested in, and one possible space is the space Fi, which is simply the space of all functions that exist on this interval I. Now, it is proved in books, we can rely on it, that this set F of all functions is actually a linear space if we add functions and multiply them by numbers in the usual way. So when you take 2 functions defined on this interval, you add them, again you get a function defined on this interval, and so on. It's easy to show commutativity, all the good laws. However, this is a really huge space, so perhaps we are wasting. Here is another popular space, Ci. This is the space of all continuous functions on the interval I. And again, it can be shown it's a linear space. The algebra is quite obvious. And we can also think about things like, okay, if I take 2 functions, they are continuous, I add them, I still get a continuous function. This is stuff from calculus. Are our functions continuous? Well, yes, because we are interested in solutions of a homogeneous differential equation, so they have to be continuous. Otherwise, my equation would not work. In fact, we need some derivatives from our solutions. So I can even go farther and I can look at a still smaller space. I can look at a space of functions that have derivatives up to the order n, and these derivatives are continuous, C for continuity. And that's a space which seems to be fitting our situation quite nicely, because all our solutions must be functions that have derivatives up to the nth one, and they have to be continuous. So this is a perfect starting point for our exploration. The space of functions with continuous derivatives up to order n. Again, it's studied in the books, it is proved that this is a linear space. So this will be the whole world, the big world. Like here, it's the 3-dimensional world, or here. And now I will look at the space, at a subset. So this is actually the beginning of the proof now. I will look at a subset, let's call it M. This is the set of all functions y, let's say yx, on interval I, that solve my differential equation. I don't really feel like copying it because it's very long, so let me just mark it as a star. Okay, that's the differential equation. I will put the specification soon. So we look at our linear differential equation, which is homogeneous. We find all the solutions, if we get lucky. We put them into a set, and we look at this set and ask, okay, what do we know about this set? And as I said, all these functions are in fact n times continuously differentiable, so M is a subset of this space. And we are going to prove, and that's the trick, we are going to prove that this is a subspace of Cn. And then automatically, it will also be by itself a linear space. And that will be part of our statement, the first half of the statement. How do we prove that some set is a subspace of a linear space? Again, we have to go to linear algebra. We essentially just need to show that this space, or this set, sorry, we don't know that it's a space yet. This set is closed under operations. So there are two operations. Let's have a look at them. The first operation is multiplication. So we have to show the following. If somebody gives us a solution, which I write like that, and a real number, in this course we work with real numbers, with real linear spaces, then the product C times Y is again a solution. Okay? So I can look at it formally from linear algebra. I just see M as some set. I don't care what kind of set it is. And I say if I take a vector from set M and a constant, then C times the vector must be also from the set M. That's what it means to be closed under an operation. But when I translate it to the meanings, it says if you take a solution of your equation and multiply it by a number, then the resulting object, a function, is again a solution of our equation. And that's exactly what I'm going to prove. So, what do I have? I have Y, which solves the homogeneous equation called star. And I have a number. And I want to show that the function C times Yx solves my equation. So how do I show that some function solves my differential equation? Well, I simply substitute into the equation and I see whether it works or not. And it's generally easier to substitute just into one side. So I'm going to substitute into the left-hand side. What do I get? I take the function C times Y and I'm substituting into my equation. So it means I have to take the nth derivative. And then I have to take the coefficient yn minus 1x, or an minus 1x, and multiply by it the n minus first derivative of C times Y. Okay? And then I take the function C times Y and I keep substituting it for Y in this formula until I get to a1x cy derivative plus a naught x times cy. That's the left-hand side of my equation after I substituted my candidate cy. How much is it? Well. Let me start from the end. I cannot really do much about this one. Perhaps I can remove the bracket. It's not really needed because there are just two multiplications in a row. So associative law, I don't have to worry. Here I have a derivative, and we know that a constant times a function, when you differentiate, the constant can be pulled out. That's calculus again. And I keep doing that with all the derivatives. So over here, I take the coefficient, and I pull out c from the derivative, from the n minus first derivative. So we know the formula probably from calculus, but if not, you just imagine that you pull out c from one derivative, then from the second, from the third, and so on, until you eventually pull it out from the last n minus first derivative. And the same trick over here. I'm pulling out c from the nth derivative. And now I look at it and I say, oh, wait a second. I see c everywhere, so I can factor it out. And what I get is y nth derivative plus a n minus 1x, the n minus first derivative of y, plus, and I keep going, plus a1x, y derivative, plus a0x, y, and that's it. So I factored c, and now I look at it, and I say, okay, what do I know? What are my assumptions? My assumption is that c is a real number, and my assumption is that y solves the homogeneous differential equation that I was given. Now I look at this, and this is actually the left-hand side of my differential equation with y substituted into it. And because y solves the homogeneous equation, then after we substitute it into the left-hand side, the outcome must be 0. So what we just did, we just took the function c times y, put it into the left-hand side of my equation, and after some work, it turns out that we get 0. What does it mean? Well, it means that c times y is a solution. So this work shows that c times y solves the equation star, and that's exactly what I wanted. End of this part of the proof. Let's have a look at the second thing that I need to do. There are two operations, multiplication by a scalar and addition. So I have to take two solutions, y1, y2, and I have to show that when I add them, I still stay in the set M. In other words, I have to show that this sum is again a solution of my equation. Let's try the same idea because it seems to work. So what we do, we substitute into the left-hand side. Now, as you can see, I don't have nearly as much room, so I'm going to do a little trick. I'm going to use summation notation, which is more convenient. So, the first term is different because it doesn't have any a with it. By the way, how come that you are not allowed to put a coefficient in front of the highest derivative? Well, the order is very important. You can also see it here in this theorem that actually the order of the equation defines the dimension of the space of solutions. Now, if I allowed some coefficient here for the highest derivative, it could easily happen that this coefficient would be 0 somewhere, and then the order of the equation would suddenly drop. And that would be catastrophic for the theory. So we are not allowed to put a constant there exactly to prevent the highest derivative from disappearing sometimes. Okay? That's just out of curiosity. So the highest derivative is different. That's why I have to treat it differently. I'm substituting the sum of my solutions, and I'm taking the nth derivative. But from now on, all the other terms have the same form. So I can simply write down a summation, let's say k, going from 0 to n minus 1. And there is the coefficient ak with variable x. And then there is derivative of y1 plus y2, and it's the kth derivative. So this is really nice, efficient, compact. Okay, what am I going to do now? I look at it and I say, okay, I'm taking derivatives of a sum, and there is a rule for that. I can simply move this derivative to each of these summands. Okay, why not? Let's have a look at it. y1, the nth derivative, plus y2, the nth derivative. That's the first term. Plus summation akx, and now I will send the kth derivative to y1, and I will send it to y2. And this term, as a whole, is multiplied by ak. That's why I had to add this bracket here. Okay, what's next? Well, I'm going to distribute this ak to the individual derivatives, and I split it into two summations using the distributive law, associative law, things like that, commutativity. Then I will gather all y1s to one heap. So there will be y1, the nth derivative, plus, and what else do I see? Over here, here are y1s with all those derivatives, and I'm multiplying them by the coefficients and summing up. So there will be a summation, k going from 0 to n minus 1, akx, and the kth derivative of y1. So that's all the y1s in my expression. How about y2s? Well, there is this nth derivative of y2. And then there is the summation, k running from 0 to n minus 1, the coefficient, and the kth derivative of y2. Okay? And I will look at it and I say, oh, wait a second. What are my assumptions? My assumption is that y1 is from the set M, so it means it solves my equation. And over here in this bracket, I can actually see the left-hand side of my differential equation with y1 substituted into it. And because y1 is a solution, when I substitute it into the left-hand side, I must get the right-hand side out of it, which happens to be 0. And of course, the same argument applies to this other bracket, because y2 is also a solution. That's in my assumption. y2 is from the set M, from the set of solutions. So this other bracket is also 0, and I'm getting 0. And I will look at what I did, and I say, oh, wait a second. I took this summation, y1 plus y2, substituted it into the left-hand side of my differential equation, and the outcome was 0. So y1 plus y2 must be a solution. Left-hand side equals right-hand side. Okay? So we just shown that the set of solutions is closed under multiplication, scalar multiplication, under addition. And that's why it's a subspace, and therefore it's a linear space. Wonderful. Now, before we move on, I'm going to make an interesting remark which is very profound, and it will come very useful. So, when we have a differential equation, we can always distribute terms to the left, to the right. And generally, there is, let's say, no unique way to do it. And that's why we don't really talk about it much. But in applications, it actually makes sense to distinguish. Very often, the differential equations have the form that there is some expression with, perhaps with x, but definitely with y, and the derivative and the second derivative and so on the left. And on the right, there is just something with x, and definitely no y's. Now, as I said, for a general equation, this can be done in many ways. For instance, let's say that you have y prime plus y times x is equal to, okay, I put x squared here, is equal to 2x. Now I look at it and I say, oh, okay, on the left I have something which has all the y's in it, and on the right there's something which has x, so yeah, it follows the prescription. But I can also subtract on x, and I get another possible rewriting into this form, or I can move both x's to the left, or I can divide here by x. And I get 1 over x, y prime, plus yx is equal to 2. So in general, I can rearrange things in many ways. But in applications, there is very often a story about the left-hand side, about the right-hand side. A differential equation describes a system, behavior of a system. And in many systems, you can distinguish between inner mechanism and outside influences. Let me show you a simple example. Let's say that you have a ceiling, a spring suspended from it, and a mass at the end. So you pull on the mass, and it starts jumping up and down, bouncing happily. So that's the inside mechanism, and it can be described by an equation which has only y's in it, as a matter of fact, and derivative and a second derivative. We will talk about it in a lecture on applications. So this will definitely come, a very nice lecture. So it's jumping, and that's the inner mechanism, something which works without my help. I just pull it, release it, and go away, and it keeps jumping by itself. So that's the inside mechanism, which is reflected in the left-hand side of the differential equation. And if I don't do anything, that on the right-hand side, it's a 0. Outside influence on the right. That's how the story goes. If I start influencing it, let's say if I take the ceiling and start shaking it around, then this would appear on the right-hand side. So that's an interpretation that we very often see, and typically we actually see it with linear equations, because with linear equations there is just one way to write them. If you want to have linear combinations on the left and everything else on the right, then there is unique situation, unique rewriting of such an equation. And then here you have the influence of the situation itself, or the mechanism itself. You are studying some system, and the system by itself has some rules or some preferences, and these are reflected in the left-hand side. And when you are solving a homogeneous equation, which is what we do over here, we want 0 on the right, we are essentially studying the system by itself. We leave it alone and just look what it does. And then when we introduce some right-hand side, it means that we are actually reaching into the system, messing with it. And we are asking, what will be the reaction of the system? So this is a very nice story. Now, when you have a differential equation which works like that, you can look at the left-hand side and think of it as a mapping. Let's say T, which actually works with the function y. How does it work? It takes the function and it does something to it. It creates derivatives, perhaps it uses x also to mess up with it, and it produces a new function. Let's have a look at it over here. Okay, I'm going to erase something and leave just the first line. I look at it, and if this were an applicable differential equation, there would be some story behind it, and it would tell me the story that the left-hand side describes some natural phenomenon, for instance, and I can call it Ty. How does it work? You take some function, you put it for y into the formula, and you get a new function. So for instance, if I take function e to x, and I apply this action of the left-hand side, then I should take the derivative, which is e to x, and I should add my function, which is e to x, multiplied by x squared. Yeah, no problem. What happens if I take e to x squared and I apply the action of the left-hand side to it? Well, I have to take the derivative, which is 2x e to x squared, and then I have to take e to x squared multiplied by x squared. No problem there. What happens to x squared? Good question. When you take x squared and you apply the action, you get the derivative, which is 2x, plus x to the power 4. Okay? So there is really nothing magical about it. The left-hand side of a differential equation can be interpreted as a mapping which takes functions and sends them to some other functions. No problem there. And solving a differential equation is something like shooting at a target, hoping that you hit it. We are trying all kinds of functions, putting them into the left-hand side and asking, what is the outcome? And we are asking, is the outcome equal to 2x? Good question. And, well, it seems that I wasn't lucky. None of these functions actually solves my differential equations because I wasn't able to hit the right target when I was shooting through using the mapping T. So that's a very interesting viewpoint, and it's very useful. But now let's have a look what happens when we have a linear differential equation. We have a linear differential equation, which means we have the nth derivative, then we have the summation, coefficients, kth derivative, and this should be, let's say, bx or 0, depending whether your equation is homogeneous or not. And I look at the left-hand side, and I can see that it's a mapping which takes a function, and this mapping spits out another function, which is given by this formula. It's the nth derivative plus summation of the lower order derivatives multiplied by some coefficients. And again, if you want, we can try to play with some examples, substituting different functions, seeing how the outcome works. Let's have a look at this proof again. What did we do? We took a function, a solution, but let's forget about solutions, okay? Let's just say that we took a function. We took a function, and we substituted into the left-hand side of our differential equation. This actually means that we substituted it into this L. But we didn't substitute it by itself, we actually multiplied by C. So this line over here actually reads L Cy. And after we played with it, we got to this line, to this part. Let's say that I put it like that. Again, this is a wave, but it's a broken wave. And this broken wave reads C times Ly. So we have shown that this mapping given by the left-hand side, when we substitute in function multiplied by a constant, then the constant can be pulled away from the mapping. And now we look at this, and we see that over here, we are actually applying the left-hand side of the equation, or the operation defined by the left-hand side of the equation, to a summation. So I can write it like that. I take L, and I substitute into it y1 plus y2. And what do I get on the output? We can see it over here. This is actually the action of my left-hand side applied to y1 plus the action applied to y2. So what did we just do? We have just proved in this proof, in this part of the proof, that if I'm given a linear differential equation, homogeneous or not, I don't care now, any linear differential equation, and if I look at the left-hand side as a mapping, then this mapping satisfies these two conditions, which means it's a linear mapping, or a linear operator, or a linear transformation, whatever way you call it. So this mapping is very, very special. And because it's linear, it means we can draw on knowledge from linear algebra. That's the beauty of abstract mathematics. You are proving properties of abstract objects that no one ever saw because they do not exist in reality. What is a linear mapping? Where do you see it? Where do you meet it? Nowhere. But when you have this abstract knowledge, you then work in some special situation, and if you find that a special situation also has these properties, this mapping is linear, then everything which is discovered in linear algebra suddenly applies to you. You can use it, which is wonderful. For instance, let's have a look again at the set M. What is the set M? It's the set of all solutions of my homogeneous equation. So it's a set, let's translate it. It's a set of all y's that when you put them into the left-hand side, they produce 0. So it's the set of all y's, so that when you put into this operator, they provide you with 0. M is the set of all y's, so that Ly is 0. There is a name for it in linear algebra. This is called kernel of the mapping L. And in linear algebra, it is proved in total generality that when you have a linear mapping, then the kernel is a linear space. So we could have proved this part of the theorem in a different way. We could have said, okay, we have a differential equation. We look at the action of the left-hand side, and we prove that as an operator, as a mapping, it is linear. And once we prove that it is linear, then for free from linear algebra, we get that the kernel is a linear space. In other words, the set of solutions is a linear space. Wow, beautiful. Notice that this would not work if the equation were not homogeneous. First of all, there is no such theorem for non-homogeneous mappings, or mappings that do not go to 0 in linear algebra. And second of all, it wouldn't work here at this stage. At this stage, we took the action of y1 plus y2, we broke it into two parts, and we got zeros which sum up to 0. But if we were solving an equation where on the right-hand side, instead of 0, there is, let's say, 13, then we would get 13 plus 13 is not 13. So that's where it would break. And also here, instead of c times 0 is 0, we would get c times 13 is not exactly 13. Yeah? So this homogeneous part is very, very crucial for this. Okay, so that was actually the first part of our theorem. And that was the part that you should be really interested in and focusing on, because that's one of my favorite questions for oral exam. I can ask for this proof. You don't have to do this story about linear operators if you don't want to. So one possibility for you is to just realize that we do it through linear algebra tricks, that we're actually just showing the closedness of the set under two operations, and you work out the operations. Or if you want, you can introduce operators, show that it's linear, and then use facts from linear algebra. It's up to you. Okay? So if you decide to go for A grade, yeah, this is a good question for grade A, I would say. So I'm not saying anything, I'm just dropping little hints. We just proved that the set of all solutions of a homogeneous linear differential equation forms a linear space, which is exactly like it was in linear algebra. And the proof actually follows the same steps. And I also teach discrete mathematics, and then I show that homogeneous linear recurrent equations, when you look at the solutions, they form a linear space. And the proof again follows exactly the same path that we had over here, because the substance is hidden in the word linear. The only thing which changes in the proof is the language of the equation. For different equations, you write different notation, but the ideas are the same. However, now we have to show something about the dimension of this space, and that's something that linear algebra does not help at all with. We have to be specific, because that's something that is specific to differential equations. And there is a neat trick. So we continue with the proof, and the trick goes like that. We fix some specific time from our interval I, and for this specific time we form initial conditions. So how do we do it? Well, we have to specify the value for y, and also for the derivative, and for the second derivative, and so on. and finally for the n minus first derivative. And as I commented, there are exactly n conditions like that. So I am going to decide to look for a specific solution which has value 1, and all the derivatives will be 0 at time x0. So there's n rows here. And then I say, oh, wait a second. I can also look for another solution which has 0 as a value, 1 for the derivative, and zeros for the higher derivatives. Now we had a theorem about existence and uniqueness, and it says if you have an interval and your coefficients are continuous there, which is here in the assumption, the second paragraph, and if the right-hand side is continuous, which is 0 in our case, definitely a continuous function, then for a set of initial conditions, there must be some solution. So there is a solution here, I'm going to call it y1. That's a solution of my equation by the existence theorem. And for this set of initial conditions, there must be a solution y2. So these are solutions. And I keep going. You can imagine how it goes. The next set of initial conditions yields y3, and I keep going. How many sets of this sort can I create? There are n rows, and since I'm moving 1 along the diagonal, there will be n different sets of initial conditions, and the last set will have zeros all the way until the last guy who is 1. And that would be the solution yn. So I have n solutions. And each of them has different values. So these are distinct solutions. But I'm claiming that actually something more is true. I'm claiming that these solutions are linearly independent as functions. So that's claim number 1. The set y1 through yn is linearly independent. How do I prove it? Well, it will be easier if I do almost a proof. Let me start with the idea. The general proof goes like that. You form a general linear combination and you assume that it's 0 as a function, and you show that the only way to get that is a trivial linear combination. The coefficients must be all 0. And it's possible, but it takes some time to see how this works. So let me show something which is not all that precise, but it's much more transparent. So if there is a non-zero, non-trivial linear combination, it means one of these functions should be expressible as a combination of the others. That's intuitively what dependence means. So let's assume that we try for y1 to be a combination of the other guys. Is that possible? Is it possible that y1 is actually a summation k going from 2 to n, some coefficients times yk? Could this happen? Let's see. I substitute x0 for the variable into this equation, into this equality. What do I get on the left? I substitute it into y1, x0, which is here, and I get 1. And here, k is at least 2, and I'm substituting into my functions yk, and because k is at least 2, it means I'm actually substituting in these columns, and I'm substituting into the function, so I'm getting all zeros. So is it possible to form some combination of zeros that yields 1? The answer is no, it's impossible. Okay, what if somebody tries to express y2 as a combination of the other guys? Could you say that you just relabel this? The answer is no. We will see it. If y2 is a combination, and now k is different from 2, alpha k, yk, then substituting x0 for the variable would not really help me, because on the left, I'm looking at y2 at my location, which is 0. On the left, I would have 0. And on the right, some combination. I can easily make some combination equal to 0 by putting alphas to 0. So this is not the right way. Instead, I'm going to differentiate. I will take derivative on the left, and I will take derivative on the right. And now I will substitute for x my initial point. Here is y2, and I'm substituting into the derivative, which is 1. And here are the other guys. So I have to look at all the other columns, not at the second column, but at the others. And I'm substituting into the derivative, so these are all 0. Is it possible to take zeros and make a combination which yields 1? The answer is no. Impossible. And now you can see the pattern. If somebody says, OK, how about y3? Could y3 be a combination of the other guys? You would take 2 derivatives. And then for y3, the second derivative is 1, but the other guys are 0, and so on. Now, as I said, if you want a full proof, which is totally correct, you don't have to do this, essentially this idea, but do it in general, which takes a little bit more work. It's not as transparent. But I hope you can see that this is doable. This is no cheating here. I'm just sort of ignoring some more difficult parts, technically difficult parts. It would take me about a blackboard to do it. So, OK, this was short and sweet. So now we have linear independence. What does it mean? It means that the dimension of my space of solutions is at least n, or perhaps more. So for my second part, I have to show that this is actually a basis. How do you get a basis? You need linear independence, and you need to show that this set actually generates all solutions. So I want to show that span of the vectors y1 through yn gives me the whole space M of all solutions. How do I do it? Well, let's take some, let's say, y tilde, any solution on interval I. Because it's a solution, it also exists at x0, so I can take all the derivatives. As a solution, it must have all the derivatives up to the order n. And I will substitute y0 into them. And in this way, by reverse engineering, I actually find which initial conditions this y tilde satisfies. So when I substitute into y tilde x0, I will get number y tilde x0. That's the number which will be sitting here in the column. So if I created another column for y tilde, I would see in this column y tilde x0, y tilde derivative x0, y second derivative tilde x0, and so on. This will be the values of my known solution. I would just substitute the proper time. And I look at it and I say, wait a second. These initial conditions can be actually expressed as a combination of these vectors. For instance, the value can be easily obtained by taking it and multiplying 1 by it. Okay? So let's have a look at what happens if I take a new function, y double tilde, and this y double tilde will be summation, k going from 1 to n, y tilde x0, yk, the kth derivative, sorry. And I have to be careful because the differentiation is shifted by 1. So I have to be really super careful. I have to write k minus first derivative. Now when k is equal to 1, I get 0th derivative, which is exactly y. And when k is equal to n, I get n minus first derivative, which is exactly the last object I have in my table. Okay? So I have a new function. What do I know about this function? It's a linear combination of solutions, and we already know that the solutions form a linear space. So this y double tilde solves my equation on I. And now again, I will cheat just a tiny little bit. What do I get if I substitute my initial time into y tilde? Well, I simply substitute here. And now I say, OK, I'm substituting x0 into my functions. So the outcome is 1 for y1, and the other guys are 0. So this is simply y tilde x0, and that's it, times 1. Okay? It's 1 when k is equal to 1, and then 1 minus 1, it's the 0th derivative. What happens if I substitute x0 into derivative of y double tilde? Well, these are just coefficients. They are not changing because there's x naught written in it. Over here, we can see it. So it's y tilde k minus first derivative x naught. And now I'm substituting here x naught, but I'm substituting into the derivative. I differentiated this equation. Now, what do I know about derivatives? Almost all of them are 0. And therefore, the only one which remains in this summation is the one when I'm substituting into y2. That's where the derivative is 1. So when k is equal to 2, I will get something out of this sum. What do I get? Well, from here I get 1, no problem. And here, when k is equal to 2, I'm getting the first derivative of y tilde. And we can keep going, looking at the second derivative, third derivative, fourth derivative, and eventually we come to the n minus first derivative of y double tilde. We substitute x naught, and we are in fact substituting into the n minus first derivative of this expression. These are constants, so we are differentiating the y's here. And the only n minus first derivative which is not 0 is the one for yn. So in this summation, we are just interested in k is equal to n, and we are getting y tilde n minus first derivative at x naught. And now we look at it, and we say, okay, y tilde and y double tilde, they have the same value at x naught for the function, for the derivative, for the second derivative, and so on. So it means that y tilde and y double tilde share common initial conditions. And we also know that they both solve the same differential equation. And now we have to go back to this theorem from the beginning of the lecture about uniqueness. Uniqueness means if you have two solutions that solve the same set of initial conditions, then necessarily they must be the same. In particular, it means that the solution y tilde can be written as some combination of y's. We have it over here. These are the coefficients. Which proves that really the solutions y1 through yn do span the set of all solutions. You can reach any solution using these guys. This means, when we put it in another way, that the set y1 through yn is a basis of the set of all solutions, and therefore the space of solutions has dimension equal to the number of the vectors in the basis, which is n. Here we go, end of the proof. Now, there are some proofs that we show in our lectures because they are educational. They showcase some ideas or approaches that are very potent and that can be used in other settings, in other ideas. They show how mathematicians think. This is not one of those. This is a very specific trick that we have here, which, as far as I know, cannot be really used in any other situation. And that's one of the reasons why I'm not going to ask for these things at the exams. But on the other hand, I think it was really neat because it shows how we use interesting ideas, combine them together. I think this is a really neat and cute proof. At least as a mathematician, I think so. Okay, that's it for our theorem on the structure of the solution set of homogeneous equations. And it really does work like in linear algebra. So now it's time to ask whether also the non-homogeneous equations behave in the right way. Let's make some room. In any theory of linear equations of any kind, there is always two structural theorems. And we already saw the first one, and we proved it. And now we have the second one, and I will show the proof. It's very educational, and also it's another of those proofs that I like to ask about when it comes to the oral exam, let's say when you are shooting for A. So I'm dropping another subtle hint. This proof can be easy or difficult. Technically, it's just 4 lines, 4 very simple lines. But the trick is in knowing what 4 lines should be written. So let's try to decipher it. Let's have a look at the preamble, the first paragraph. We start with some yp, which is a particular solution of a given linear differential equation. So here we go. Proof. and we have yp, which solves our differential equation. So how does it look like? Well, it's the nth derivative, and then there are all the other derivatives, including the 0th one, multiplied by some coefficient. And this is equal to, and let's see, do I see the word homogeneous in the preamble? No. So we have to put bx, a general case. In fact, I can expect this equation to be non-homogeneous because for homogeneous equations, this theorem does not really help very much. So we have a non-homogeneous equation, and we found some solution of this equation because we got lucky. This is hard. Okay, we should be careful. This is happening on some interval I. Now it's mathematically correct. We always, when we have solution, we have to specify region of validity, always. To simplify my life, I will take this right-hand side, and I will assume that it defines some mapping, Ly. L stands for linear or for left-hand side, okay? So that's the assumption of this theorem, a general assumption, universal assumption. And now we look at the main statement, which is the middle paragraph. A function is a solution of this equation, meaning this one, if and only if. Okay, this is where we stop. If and only if, that means equivalence. There are two parts, and they are equivalent, which means that there is implication going both ways. And that's exactly how equivalences are also proved. We have to look at two implications. And in this case, it is actually easier to start with implication that goes backwards. So we start reading this statement from the end. Let's see. What do I see there? I see YH. YH is a solution of the associated homogeneous equation. So I ignore the right-hand side. I put 0 there, and I find a solution. YH solves, and now we can write it easily. Ly is equal to 0. That's very convenient, on I. And what do I want to do with this YH? I want to take this YH, and I'm going backwards. I'm adding it to the particular solution, and I get some function Y naught. And the claim is that this Y naught actually solves the original equation. So I want to show that then Y naught, which is Yp plus YH, solves Ly is equal to Bx on I. So that's one of the two statements that we have to actually prove. So this part, this analysis is very important. First, we are beginning to understand what really this theorem says, and I will talk about it a little bit more. And secondly, it actually gave us a statement which can be proved rather naturally now, because we have our assumption here, YH, which solves some equation. We have another assumption which is general, and we want to use these pieces of information to show that some function solves a specific equation. So how do we show that some function solves a specific equation? The most natural way is to simply substitute and see whether it works or not. So we try it. We take the left-hand side of our equation and we substitute into it Y naught. What is it? Well, it's Yp plus YH. Now we proved previously that this L as a mapping is linear, and therefore we can split it into two parts. We are applying L to Yp plus we are applying L to YH. And now let's have a look at our assumptions. What do we know about Yp? Yp solves the original equation, so when we put it into L, the outcome should be Bx. That's the outcome of this part. YH solves the homogeneous equation, so when we put it into the left-hand side, it should yield 0. And the outcome is Bx. That's the outcome of left-hand side applied to Y naught. And this shows that Y naught really solves Ly is equal to Bx. And that's it. That's the end of the proof. Yeah, okay, perhaps this is not 2 lines, but it's short, 4 short lines or 3 short lines, okay? What does this really say? Let's think about it. It says 2 things. Let's have a look at it first from the point of view of linear algebra. in the previous theorem, we have shown that when we look at the homogeneous system, then the solutions form a linear space. Like that. So the solutions YH, they are here. And now I take those solutions YH and I shift them by this one solution YP. I'm shifting all of them. There are many solutions that solve the homogeneous equation, and I'm shifting all of them by the same YP. So in fact, I'm taking the whole subspace and I'm shifting it in this direction by this displacement. So I'm getting a new set of functions. And it says here that these new guys are also solutions of the original equation. So if this was the set of solutions of the homogeneous equation, then these are solutions of the original equation, which I obtained just by solving it once. I found one solution and used it to shift this set to get many solutions of this original equation. And this exactly agrees with what linear algebra had for linear equations. We can also see it as a practical guide for finding solutions. We will see that solving non-homogeneous equations can be hard, really hard. So when we are really lucky, we can find one solution. But we want to know all solutions. That's the typical trick. We want to know a general solution. So this actually says, don't worry about solving the non-homogeneous version. You just find one solution somewhere. And once you have one solution, you can stop looking for more solutions. Instead, you focus on the homogeneous equation, and you get complete information. You start finding solutions of the homogeneous equation, and we will shortly see in the next lecture that this is actually very simple. And once you know these homogeneous solutions, you can use them to modify this particular solution which you found somewhere, and it will generate new solutions for you. So this is a machine for generating solutions of the original equation. Wonderful. There is one piece missing. We can generate solutions, new solutions of the original equation, but we want to know all of them. Is this way of generating new solutions exhaustive? So if we take all these YHs and shift them, do we get all solutions of the new equation, of the non-homogeneous one? Or could it happen that there is some solution floating somewhere around here which is separate, and I missed out on it, which would be very unpleasant, by the way? So that's a very good question, and that's the second part. Now let's read it left to right. When somebody gives us a solution of the original equation, then it comes in the form yp plus yh for some homogeneous solution. So this statement really says, when we read it left to right, that this way of generating solutions is exhaustive. It captures all possible solutions, which is wonderful. So what we have to prove is this. If y naught solves the original equation, then there must exist some solution yh, which is a solution of the homogeneous version, and it generates this solution y naught in the usual way, in the way that we are interested in here. So that's the second statement that we have to show. Two implications. One implication here, second implication here. And how do we show it? Again, let's ask what we have to do. Well, this time it will be actually a little bit more difficult, because it's an existential statement. It says there is some function, some mysterious yh, which satisfies certain conditions. Typically, when we are proving existential statements, we are doing it by exhibiting an example. So, where do we find some yh? What do we have in store? Well, we have yp at this moment. We always have it. That's the particular solution that we have all the time in this proof. And now we also have another solution of the original equation. We have two solutions. And we are trying to find a connecting piece. Well, we can simply try to go the path of the least resistance. We are looking for a specific function that works in this way. So why don't we just think for a second which function would work like that? We try to take yh is equal to now, what function would do the trick? We are looking for a function yh so that when we put it here, it will eventually provide us with y0. So we can essentially solve this equation for yh, and it will tell us what the candidate is. It's y0 minus yp. That's our candidate. Is it a function? Yes, these two guys are functions, so it's a function. These guys are solutions, so they must have n derivatives, and therefore this guy also has n derivatives. So far, so good. How about these two conditions? We try to take yh, and we check that it does what we want from it. Then yp plus yh is simply yp plus y0 minus yp, which is y0. This checks. So this function that we found really satisfies the second condition, and we are not surprised because we actually fixed it in that way. We chose it like that. The second part will be crucial because we chose this yh based on some algebra, but we have to show that it solves the homogeneous associated equation. So we take this yh and we put it into the left-hand side of our equation. What do we get? Well, yh is y0 minus yp, and this L works as a linear mapping, so we can split. And now we say, okay, y0 is a solution of the original equation. So Ly0 has bx on the output. That's what it produces. And if I put yp into the left-hand side, then again it must produce bx. That's what we see over here. And therefore the overall outcome of this procedure is 0. And we have just shown that yh indeed solves the associated homogeneous equation. And we are done. End of the proof. Wonderful. Before we finish, because that's the end of the structural part of this chapter, let me go back to this stage. What if you are trying to show a proof, let's say on an exam, and you don't feel like working with L because you didn't introduce it before and you don't want to bother introducing some L into the game? What would you do? Well, we want to show that this yh solves a specific equation, so we simply substitute into the left-hand side. So that would be the alternative. We take yh and we substitute into the left-hand side of our equation. What do we get? Well, yh nth derivative plus summation akx yh the kth derivative. And then we say, okay, what is yh? For yh we have this formula which we dreamed out. So here we go, nth derivative plus summation akx y0 minus yp, kth derivative. And then we say, okay, the differentiation is linear, so we can simply distribute it here, we can distribute it here, and here, and we get y0 nth derivative minus yp nth derivative plus summation akx y0 kth derivative minus yp kth derivative. This is getting long. You see how nice this L is. Anyway, now we break this bracket over here, we multiply out, we break the sum into two sums. We do all the stuff that we did before, and we gather all y0s in one place. So it will be y0 nth derivative plus summation akx y0 the kth derivative minus yp the nth derivative plus summation akx yp the kth derivative. And then we argue, okay, y naught is a solution of the original equation, and this is the left-hand side, so this must yield the right-hand side. And yp also solves the original equation, and you are getting 0. So this can be done without this linear algebra business, just on the elementary level. And if you do it like that, yeah, that's a correct proof, no problem with that. Actually, okay, I didn't want to bore you, but there is something I probably didn't comment enough on before. We are always asking about validity of solution. Solution on interval I. So here, these equalities, these are actually equalities between functions. We are comparing functions here. And when we are comparing functions, we are always comparing them on some sets. So all these calculations, when we are passing from one expression to another, this is actually functions, and we are doing it on the set I. So I can imagine that I'm substituting x here and x here also into those derivatives. Properly, we should put this here. Just people are lazy. They don't do it. But we can actually see over here the variable x everywhere. And the statement is that whenever we take x from the interval I, then this is actually equality of numbers, because we are substituting some particular x into functions. So these are numbers, and these numbers are equal. Okay? So that's how it works. This is just a technical remark. Now, as usual, we are really interested in a general solution, a formula which would capture all solutions of the given non-homogeneous equation. And if we look at the statement that we proved here, we can imagine that we are shifting those yh's all at the same time. We look at the group of all the yh's and shift them, just like the linear algebra picture shows. So mathematically, we can imagine that we have a formula which describes all the homogeneous solution. In other words, we have a general solution for the homogeneous equation. And when we have it, we just add yp to it, and we get a formula which captures all solutions of the given equation. So again, that's a practical point of view, and that's the third paragraph in the statement that we can see over here. And we will use it. Definitely we will use it when solving differential equations. And that's about it. So now we have the structural theory for linear differential equations done. And the next step is actually figuring out how to solve them. So we will see.